There we go. Okay, welcome everyone to another weekly live. I'm so happy that you're here. And this is another great thing that we're going to be doing. Cooper is going to be the one leading you today on more topics from general chemistry that you need to remember before walking into your lecture for Organic Chemistry 1. I I'm glad that you're also going to get a little bit of an intro to what you see later on, like the first topic that you cover in organic chemistry, because that just means that you guys are going to be ahead. And if there's a curve, that means you have a better likelihood of being that person who like ruins it for everybody else. And then you're the one on top of the curve. So which feels amazing, but you don't want to tell anybody. But I know that this is going to be beneficial for you to understand that. And yeah, so I did want to mention real quick that in the actual in communities community, there is a page there. There's like a specific thread specifically for the weekly live tutoring that you can ask questions. And you have access to that. That actually, pings you or notifies you once you're on community. And there you'll be able to ask questions for every single week's live. So on Thursday, that's going to go live again on that community page. And then that's where Cooper will decide, okay, I can answer these questions on the next live. So a lot of this is like because you're a community member, and specifically if you become a premium member, you'll have the ability to control what is going to be talked about, what's going to be taught, what's going to be answered, and actually get your questions answered. So that's the beauty of this. And you will see that again going live on Thursday for the next following Monday's live that Cooper will be leading again. So let's just jump right in. Cooper is a new addition, if you didn't know, to our community team, and he'll be running these weekly live tutoring sessions for this entire semester. So take it away, Cooper.
Sweet. Alrighty, y'all. We'll go ahead and just. But like Melissa said, the first thing we're going to cover will be bond line notation. You may or may not have learned it in at the end of General Chemistry 2. But even if you didn't, we're going to take a hot second, go over it, give you a brief introduction. So like Melissa said, when you walk into the first class, you already feel prepared. And then after that, we're going to review some of those orbitals, whether it is atomic orbitals, kind of reviewing those S&P orbitals, and then hybridized orbitals, which are the main ones we use to form bonds. And then at the very end, we'll just go through a very brief introduction of resonance and what you should expect when it comes to organic chemistry. But yeah, we'll dive right into our first thing. So in terms of bond line notation, last week we covered and we reviewed Lewis structures in terms of how our individual bonds will be bonded together and how to draw them and formal charges and all that stuff. So if we remember from Lewis structures, this is generally what they look like, where we can visually see our atoms being bonded together. Now, in terms of this one, this is a good example of what's called hexane, which is our six carbon structure with 14 hydrogens. And if we're looking at the Lewis structure, I will say if we were to continuously draw that out every single time, it would get a little tedious after a while. So what we'll be exposed to in organic chemistry, especially since we'll be drawing a lot of molecules, is what is called bond line notation. Now, the plus side and advantage of bond line notation is that number one, it's a lot easier to draw. And number two, we can easily see the actual 3D geometry, if you will, a lot easier as opposed to Lewis structures. Now, in terms of bond line notation, the trickiest thing to get used to at first is understanding where your carbons are. So when we are using bond line notation, we can use either the corners or the ends of our molecules to represent carbons. So what do we mean by that? The easiest carbons to visualize at first will be those end carbons. So if we're looking at our bond line notation, this end portion of the structure, these will be their own individual carbons. And if we compare it to the Lewis structure just above, we see our N carbons are highlighted in red, and yet again, they're right here. Now, in terms of our internal carbons, if you will, we can think of those as corners, which if we highlight it like this, the part I just circled, we can think of that part as a corner. Or another way of viewing it will be the intersection of those lines. So we can see these two lines intersecting at this singular point right here. So that will be one of our carbons. So that will be how that's how we can read where our carbons are in the bond line notation. And one of the things about bond line notation, especially when we're looking at those single bonds, is that we want to draw everything in a zigzag formation. And just to review what a zigzag formation is, it just looks like that. We're just doing a simple zigzag. And the reason we draw it using that notation, we want to show the zigzag formation, is just because that's what the actual 3D structure looks like. So right here is a simple molecule. I will say the one on the slides does have 6 carbons. This one only has 4 carbons, just so it's a little easier to view. But those black atoms right there, those are our carbons. And we can see the zigzag formation that it forms just because of Vesper theory. So that's why we're showing it using a zigzag formation. So that's the first part of bond line notation, is just understanding where those carbons are. And the next thing we have to assess is how those carbons are actually bonded. So what we just reviewed, we looked at hexane, and each individual bond in hexane is just a single bond. But we could also have a situation where our carbons actually have a double bond between each other, and this is what it would look like. So if we were to count our carbons, we still have 1, 2, 3, 4 carbons. And yet again, one of the ways we can assess everything is by looking at the intersection of our lines, and those will be our carbons. But between these two carbons, we add in that extra line, which showcases that we have a double bond between these two carbons. And what's also nice, which we'll kind of reiterate when we're talking about hybridized orbitals, is yet again, when we are using bond line notation, it's actually showing the geometry. So if we're looking at a single bond, we have our tetrahedral geometry. If we're looking at if we're looking at double bonds, we're showing that trigonal planar geometry. One way to show that kind of triangular shape is if we were to add in a hydrogen right here, we can see our triangle right there. And then lastly, if we're looking at those triple bonds, we have a linear geometry. Now, triple bonds, I will say, can be a little confusing at first in terms of assessing where your carbons are and how to draw them. So in terms of counting our carbons, the end of the molecule is definitely the easiest part to see, because if I circle these two ends right there, those are 2 carbons. But in terms of our internal carbons, we can look at it as the intersection of these lines right here, or we can think of it at the ends of those triple bonds that we have shown. So right here is 1 carbon, and then right here is another carbon. So in total, we have 1, 2, 3, 4 carbons overall. I will say one of the most common mistakes that students do make in terms of drawing triple bonds is showcasing a slight zigzag in the structure. And this is very common only because when we are drawing molecules, whether it's single bonds or double bonds, we still end up drawing that zigzag formation. But for triple bonds, which we'll review a little later in this lesson, they have a linear geometry. And since they do have a linear geometry, we have to draw them as straight, like shown here. And we know that it will be incorrect. Just say if we have a carbon right here, which we do, if we're like having a slanted line coming off of that carbon with a triple bond, that's how you know that you may have made a mistake while drawing it. So whenever you have an atom branching off of our carbon with the triple bond, it should have a straight line that branches off of the molecule. Now, besides looking at the carbons, the next thing we have to assess when drawing bond line notation is that we have to assume that the hydrogens are already there. So yet again, if we're looking at Lewis structures, if we were to continuously draw this over and over again, it would get tedious. And if we were to draw a similar version of bond line notation and we were to include every single hydrogen, Yet again, it would be very time consuming and it would be tedious. So what we can do is if we're looking at bond line notation, we can just assume that that the hydrogens are already there. So how do we know and how can we figure out where our hydrogens are? It all depends or it all is based off of neutral carbon wants for bonds. So let's look at this carbon right here in blue. And we know if we are looking at this example up here, that there should be two hydrogens coming off of that blue carbon. And the reason we can figure that out is if we look at our carbon and we ask ourselves, how many bonds does that carbon currently have? It is branching over here to one carbon, and it's also branching to the right to another carbon, and it currently has two bonds. So in order for it to have four bonds and for that carbon to be neutral, we would have to include two more hydrogens for it to be neutral and for it to have four bonds. So yet again, just to recap, since this carbon was branching off to two other carbons, it needed two more bonds in order for it to have a total of four. And then just kind of doing another example, if we're looking at our N carbon right here in green, that carbon currently only has one bond going over to that blue carbon. So if we wanted to make it neutral, we would have to include three more bonds, and those bonds would be to hydrogen. So yet again, we can just assume that they are there based on how many bonds carbon currently has. And then one last thing as well is that whenever your hydrogens are bonded to your carbons, that's when you assume that they are there. The only time you cannot assume that they are there is when they are bonded to heteroatoms. And heteroatoms are basically any atoms that are not carbon or hydrogen. So if you're looking at nitrogen or oxygen, those are good examples of heteroatoms. And then one last thing about bond line notation before we dive into some of our examples is that lone pairs can also be assumed that they are there. So if we're looking at this oxygen, we know that it's neutral because it's not showing us that there is a charge. And oxygen, whenever it's neutral, has two bonds, which we can see right here, and then it would need two lone pairs added in for it to be neutral. And yet again, we can use formal charge to help us out. So in this case, our formal charge is 0 because we don't have a charge assigned to that oxygen. And yet again, our equation to help us find formal charge is your valence electrons minus your lines and dots. And just to review that, oxygen should have 6 valence electrons. And if we were to count our dots and lines, we have 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0, meaning our oxygen is neutral. So yet again, if you need to assign lone pairs or you're just curious on how many lone pairs a molecule has, use the formal charge equation to help us out. And we'll go through examples to kind of showcase what that looks like in terms of finding our structure. But for our first example, we will be converting our Lewis structures into bond line notations. And now that I'm going over these examples, if you do have a question, feel free to put it into the chat and I will get to it when I can. But for our first one, if we're looking at our structure, I think the best place to start would be our cyclic structure, only because if we're using bond line notation, we can go ahead and draw out those lines nice and easy. We'll just double check our carbons later on. But if we're looking at this part of the structure, we have a hexagon. So what we can do is just go ahead and draw that out. There we go. So right there, we have our hexagon. And I will say, as we are converting structures into bond line notations, one of the things I like to do is to count the number of carbons I have and just make sure it aligns with the Lewis structure that we were given. So for example, this Lewis structure, in terms of the cyclic portion, has 6 carbons. 1, 2, 3, 4, 5, 6. And if we were to count our carbons right here, we have 1, 2, 3, 4, 5, 6. Yet again, whenever we have those lines intersecting, those are our carbons. Now, the next thing we can do for that cyclic structure is add in those double bonds. So we can start with these two carbons right here. is we can see that it has a double bond because we have those two lines. So we'll go ahead and include that double bond right there. Make it look a little nicer, maybe. Perfect. So we have our double bond here, which we can see how those two carbons are correlated. And then we can go through and add in our next double bond. We see that it's between these two carbons. And if we were to showcase where those carbons are on the bond line notation, they're right here. So we'll go ahead and add in our additional line to showcase those carbons have a double bond. And then for our next double bond, we have these two carbons right here. And yet again, on the bond line notation, they're between those two carbons. So we'll go ahead and include that. Now that we have our cyclic structure, we can go ahead and include the branches that are coming off of it. So the easiest one to start with will be this NH2 group, just because it's a smaller group compared to this whole thing. So our NH2 group is all the way at the bottom portion of our cyclic structure, which is highlighted right here on our bond line notation. And we'll go ahead and include that, NH2. And yet again, since we're using bond line notation, we don't necessarily have to include the lone pairs because we can assume that they are there. Now, up next, we'll go ahead and include that whole portion of the structure. And just to recap, and to make sure we know where that carbon is, we can see that it will be 2 carbons away from the carbon that's bonded to our NH2 group. As we see, we have 1, 2, 1, 2. So this carbon right here will have this branch coming off of it. And we can see that if we're looking at the Lewis structure, this carbon is bonded to a carbon with 2 hydrogens. So we'll go ahead and include that. But currently, this carbon has 3 hydrogens coming off of it. And that's not the case because if we're looking at the Lewis structure, the carbon should be bonded to an oxygen as well. So we'll go ahead and include that. We have our oxygen. And then looking at the Lewis structure, this oxygen is being bonded to a CH3 group. So all we have to do is just draw out one single line, and then that is our Lewis structure. Or sorry, our bond line notation. So just by doing that, we can see that visually, this structure is definitely a lot easier to draw as opposed to this large Lewis structure. And yet again, with this oxygen, we didn't include the lone pairs just because in bond line notation, we don't have to.
And I'm going to interrupt for 1 second, Cooper.
Yeah.
Just as you guys may know, this is also being streamed on YouTube, and we just had a couple questions on YouTube, and I wanted just to clarify that those watching this on YouTube, the people who are able to ask questions directly to Cooper and have that is community members. So that's a huge reason and benefit of being a community member, especially a premium member, because all semester long you will be able to ask your question, and Cooper will be answering that on the live weekly tutoring sessions. So if you want to ask questions and be part of this actual live stream and have the ability to ask questions, then join community. And for those of you who, of course, are actually in the call right now, are community members, at any point, please feel free to ask any questions in the chat, or you could even unmute yourself and ask the question directly to Cooper. So carry on, Cooper. You're doing great.
Sweet. Yeah, like Melissa said, please, if you guys do have questions, please ask me. I love talking about this stuff, but besides that, we will just go ahead and dive right back into it. So yet again, we are given another Lewis structure, and we have to convert it into bond line notation. And I will say, whenever I'm given a Lewis structure that has a decently large carbon chain, if you will, the first thing I will start with is the longest carbon chain, and then later I will add in the groups that are branching off of the longest carbon chain. So what do I mean when I say the longest carbon chain? That just means the longest part of the molecule with the most carbons in a row. So in this molecule, the longest carbon chain will be right here, as we have 4 continuous carbons bonded to each other. And then the groups coming off of that carbon chain will be this group right here, and then this larger group that I just circled, which kind of keep that thought process when we start talking about nomenclature, but that'll be for another lesson. And whenever I start with the long carbon chain, or just any carbon chain in general, the first thing I do is assess how many carbons there are. And then that helps me easily draw everything out because there's a little tip I can give you that whenever you're drawing longer molecules, you want to draw one less line than the number of carbons that you have. So this comes in handy when you're dealing with structures with like 6, 7, 8, or 9 carbons. But in this case, we can easily use it to draw out our structure. So in this case, our longest carbon chain has 4 carbons, which means to easily draw the bond line notation, all I need to do is draw 3 lines to showcase that 4 carbon structure or portion of the molecule. So I'll draw 1, 2, 3. And yet again, don't forget that that will be in the zigzag formation to showcase our geometry. And if we were to go through and to count those carbons, we have 1, 2, 3, 4, 1, 2, 3, 4. So that's just showing us that by drawing one less line than the number of carbons we were given, that's an easy way to draw out that carbon chain a lot faster. Now from there, since we have our longest carbon chain, I'm going to go through and just count some carbons just to make sure I'm assigning all the groups to the correct carbons. So if we're going through, we'll assign this one as carbon 1, 2, 3, 4. And I will say, for those of you who may be familiar with IUPAC nomenclature, this is not necessarily going by any nomenclature rules. I'm just going through and counting the carbons in order just from left to right. But if we're looking at our longest carbon chain, we see that carbon 2 has a double bond to an oxygen. And if we were to count our carbons starting from left to right, we have carbon 1 and then carbon 2. So on that second carbon, we'll go through and add our double bond to oxygen. And then for our next group, we see that it's coming off of the fourth carbon. So if we were to count, we have carbon 1, 2, 3, 4. And since this is our fourth carbon, it should be bonded to that oxygen. So we'll go ahead and include that. And then if we were to complete the molecule, we see that the oxygen has a bond to another carbon, which is being bonded to another carbon. So we'll go ahead and include that as well. Perfect. And then just to showcase where those carbons are, this carbon right here is similar to that one in the Lewis structure. And then we have our end carbon right here. Perfect. And then one thing I will note in terms of just becoming familiar with terms that come from organic chemistry, this group right here, that end portion is what is called a methyl group. And whenever you have a methyl group, that'll be looking at a CH3 group, which is very common at the very ends of a carbon chain, which we can see here. That's what it would look like in more so a bond line notation. Moving on to our next structure. So here we definitely have a smaller molecule with also a smaller carbon chain. And if we were to use our rule from earlier, draw one less line than the number of carbons you have. Since we have 3 carbons in a row, that's our longest carbon chain because those are the only carbons in the molecule. Since we have 3 carbons, all we have to do is draw 2 lines and we now have all 3 carbons. 1, 2, 3. Now, if we were to add in our groups, which in this case, we have a double bond between our carbons, and then we have a double bond between oxygen with another OH group coming off of this carbon. This is a great example of what are called functional groups. And in this case, this is a carboxylic acid, but we will review functional groups a little later in the month, most likely. But adding in our groups, we see that these 2 carbons have a double bond. So we'll go ahead and include our extra line to showcase that those carbons do have a double bond. And then we see that our third carbon at the very end does have a carboxylic acid, or I should say is a carboxylic acid, which means it will have a double bond to oxygen, along with another single bond to an OH group. And another tip I can give you guys, especially when you are starting out with bond line notation, is just when in doubt, count it out. It is very common, especially early on, for students to maybe miss a carbon just because If you're continuously drawing out those zigzags, you may just end up forgetting one or adding too many. So whenever you're converting, whether it's a molecular formula or a condensed formula or a Lewis structure into a bond line notation, just always take the extra step and double check that you have the correct number of carbons and that you have the correct number of hydrogens, which these next examples will be really good for. So for these ones, excuse me, what we want to do is count the total number of carbons that we have in our molecules. We want to count the total number of hydrogens that we have in our molecules. And then also, if we have any heteroatoms, such as oxygen, nitrogen, whatever it may be, we want to include any lone pairs where they should be. And that also counts with carbon as well. If carbon has a positive or a negative charge especially, we should be including those lone pairs. Now, for this first one, I think we should start off with counting our carbons because that will be the easiest thing to find. So we'll start at the very end. We have 1, 2, 3, 4, 5 carbons in total. So go ahead and write that down. And yet again, where our carbons are at the very end of the molecule right here. And then wherever those lines are intersecting, or our quote unquote corners, if you will. And then in terms of hydrogens, we'll go ahead and actually draw these out just because hydrogens as well is another tricky thing just to get used to when you're looking at a bond line notation and trying to correlate how many hydrogens each atom or carbon has. So we'll start with our end carbon right here. Since this carbon only has one bond going off to another carbon, we'll go through and add in 3 hydrogens just so the carbon has a total of 4 bonds. And then looking at this carbon right here, it currently has 2 bonds going off to other carbons. So we'll go ahead and include 2 hydrogens just to give it a total of 4 bonds. And then this is our first time assigning a hydrogen to a carbon that does have a double bond. So if we're looking at this carbon, it currently has 1 bond going over towards the right, but then over here, it has 2 bonds that has a double bond to our carbon right here. So in total, this carbon is currently showing that it has 3 bonds. So we'll go ahead and include 1 hydrogen so that it has a total of 4 bonds. And then that'll be the same with that carbon right there. We'll add in an extra hydrogen. But what about this carbon? Does that carbon have any hydrogens? No. Only because if we were to count the total number of bonds it has, it currently only has 4 bonds, so that means it's happy. And to showcase those 4 bonds, we have 1, 2, 3, 4. So in terms of the total number of hydrogens we have 1, 2, 3, 4, 5, 6, 7. Don't forget, we're not just counting the total number of hydrogens that are coming off of the carbons, we also have to include the hydrogens coming off of our nitrogen over here as well. So since we had 7 hydrogens coming off of our carbons, and we only have 2 hydrogens coming off of the nitrogens, that means we have a total of 9 hydrogens in our molecule. Now, the next portion of this question is we have to include any lone pairs wherever they need to be. So in this case, we just have to be aware of any charges our molecules have, and then also if we have any heteroatoms, should they have lone pairs if they're neutral or not. So for example, if we're looking at this oxygen, neutral oxygen will have 2 bonds and 2 lone pairs, and since there's no charge right there, we know it's neutral. So we'll go ahead and add in our 2 lone pairs. And then yet again, if we were to go through and use our formal charge equation to show that it's neutral, oxygen has 6 valence electrons. And if we were to subtract that with our dots and lines trick that we used, we have 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. So our oxygen is neutral. And then similar concept with this nitrogen, but this time neutral nitrogen enjoys having 3 bonds and 1 lone pair. So we see that it has 3 bonds, 1 bond going to this carbon right here, and then it has 2 bonds to hydrogens, which is meant by that NH2. That's just telling us it has 2 bonds to other hydrogens. So in order for it to be neutral, we'll go ahead and include those lone pairs. Perfect. So for our next question, we'll be doing the same thing, counting the carbons and the hydrogens. So starting with our carbons, we're looking at those corners and the ends of the molecules if we have any. In this case, we have 1, 2, 3, 4, 5, 6, 7 carbons. And then in terms of the hydrogens, we'll also go through and count those and include those in the molecule. So just say if we're looking at this carbon right here, the carbon currently has 1, 2, 3 bonds, which means if we include a hydrogen right there, it is now neutral. And all of these carbons are similar in terms of how many hydrogens they need, just because all of these carbons have 3 bonds. So we'll go ahead and include our extra hydrogen for all of those carbons to show that all those carbons have 4 bonds. And now that we're showcasing that, we can go through and look at this carbon next. And as a reminder, this carbon has no hydrogens branching off of it because this carbon is already happy and it has those 4 bonds. So if we were to count, we have 1, 2, 3, 4 bonds. But looking at this carbon right here, it currently only has 2 bonds, one to our carbon over here and then one to our oxygen over here. And that means we would include 2 hydrogens in order for it to be neutral. And then if we were to go through and count our hydrogens, we have to make sure that we include these 3 hydrogens that are being bonded to our oxygen. So if we were to include that, and I will say this should actually be a 2 right there, just because if we were to have 3 hydrogens coming off of it, that would kind of give us a really wonky formal charge for oxygen, and it does not want that. So we'll go ahead and count our hydrogens. So there should only be 2 hydrogens coming off of this oxygen right here. So we have 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. Perfect. And then in terms of assigning our formal charge, let's go ahead and draw out what this would look like. We would have our R group, and yet again, an R group we can just think of as the rest of a molecule. So whenever we have an O2 group with a positive charge, it looks like this, where we have our positive charge. And now what we have to do is include our lone pairs. Now, if we remember, whenever oxygen has 3 bonds and 1 lone pair, that's when it's going to have a positive charge. So this oxygen will have 1 lone pair. Perfect. Now, for our next example, it's definitely a larger molecule, but we'll start with our carbons. We're looking at the ends of the molecules and also those intersections. So we'll start here at the very end. And even though this is a double bond, we still count this as the end of a molecule. So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons in total. And then in terms of our hydrogens, we'll go through and include those as well. So if we're looking at this carbon, we've never seen a double bond at the end of a molecule, but this carbon currently has 2 bonds. So we'll go ahead and include those 2 hydrogens to make sure the carbon has 4 total bonds. And then this carbon currently has 3 bonds. So we'll go ahead and include in that hydrogen so that it has 4. And then same thing with this carbon right here. It has 3 bonds to other carbons. We'll include our hydrogen. And then this carbon down here, since it only has 1 bond to another carbon, that is a methyl group, so we will include our 3 hydrogens. Perfect. And then these 2 carbons right here, they're branching off to 2 other carbons each, which means those 2 carbons will both have 2 hydrogens coming off of them. We'll go ahead and erase that real quick. Perfect. But what about this end portion right here? We'll go ahead and actually include the lone pairs real quick. But since this part has a negative charge, that means that the carbon will have a lone pair. So carbon, whenever it has 3 bonds and 1 lone pair, that's when we get a negative formal charge. So we will include those 2 lone pairs at the very end. And then we'll go back to the hydrogens. We'll go through and count all of them together. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. So yet, if we were to actually draw out all of those hydrogens, and if we were to draw out a Lewis structure for this especially, we would see how time consuming that would be. So this is a good example of how bond line notation is very efficient when drawing molecules. Now, up next, we're going to talk about atomic orbitals. And in terms of atomic orbitals, just to refresh your memory, those will be regions of space where we can find our electrons. And in terms of organic chemistry, I know that in Gen Chem, we looked at s orbitals, p orbitals, f orbitals, d orbitals, all of those orbitals. But in OChem, we're mainly focusing on s and p orbitals. And in terms of those s and p orbitals, we're looking at the valence shell, which are going to be those outermost electrons. We're not really concerned about those innermost orbitals if we're looking at something like carbon or oxygen. We're mainly focusing on the valence shell, which, to refresh your memory again, those valence electrons would be your outermost electrons of an atom, and those are the ones that are participating in bonding. So in terms of s orbitals, those will be your spherical type orbitals that kind of just look like a circle. And in terms of our p orbitals, we will have three of those. And the reason we have three of them is because they all lay on different axes. So for example, one of the p orbitals will be on the x-axis, one of them will be on the y-axis, and one of them will be on the z-axis. And in terms of energy, whenever we're looking at s orbitals, those will be a little lower in energy than our p orbitals, which will be higher in energy. And the reason they're higher in energy is just because we can see that they're a little more dispersed and further away from the nucleus. So for our atomic orbitals, this is also a good introduction into sigma bonds and pi bonds. So if we can refresh our memory, sigma bonds are going to be those strong bonds that have head-to-head overlap, as opposed to pi bonds, those will be bonds that have a very weak, kind of like side-to-side overlap. And a really good analogy I like to use to showcase the differences between these is just by using a tennis ball. So we can think of my arms as p orbitals, and I'll showcase a sigma bond between p orbitals where they have head-to-head overlap. So just say if my fists are the lobes of those p orbitals, and we can think of the tennis ball as an electron. So if they have head-to-head overlap, the orbitals are just in the same space that electron is in, and we can see they have a very strong overlap. That bond is not breaking. That bond is not going anywhere. So this is a good example of sigma bonds. But just say if we're looking at pi bonds, those are when you have those adjacent orbitals. And that is one thing to note, that you can only get pi bonds from p orbitals. So we have our two p orbitals right here. They're currently adjacent to each other. And in order for us to have side-to-side overlap with the bond, we don't have that head-to-head overlap like we just did. But in order for that electron to get over to this p orbital over here, think of it as like I'm throwing the ball back and forth to each other. And now, the reason that that is not as strong as both lobes holding it together is because just say as when I'm throwing that ball back and forth, it can easily be knocked out. So that's a good representation of why pi bonds will be a little weaker than sigma bonds. And in terms of finding sigma and pi bonds within a molecule, every single bond will have a sigma bond. And one way I think about it is single is equal to sigma. In terms of double bonds, double bonds will have one sigma bond and one pi bond. And then triple bonds will have one sigma bond and two pi bonds. So we'll get comfortable with that with our examples. So for the following molecules, what we want to do is find how many sigma and pi bonds are in the molecule. And then also we want to count how many p orbitals each molecule has. And more specifically, when we're talking about p orbitals, we're talking about unhybridized p orbitals. So we'll write that down just to clarify. Only because as we get a little later in this lesson, We can have p orbitals that are hybridized, but we're talking more specifically about the unhybridized one, which yet again participates in those pi bonds. So in terms of sigma bonds, what we can just do is count every single bond in the molecule, and that will count as one sigma bond. So we have 1, 2, 3, 4, 5 sigma bonds currently. But if we were just to count those sigma bonds, we're still leaving out all the hydrogens that are branching off. So we'll go through with some extra practice of including those hydrogens just to make sure we're comfortable. So if we're looking at the end of our molecule, to refresh your memory, this is a methyl group, which means we will have 3 hydrogens coming off of it. And that carbon is now happy because it has 4 total bonds. And then in terms of these 2 carbons, since each of those carbons currently has 3 bonds, we will include 1 hydrogen for each of those carbons to give it a total of 4 bonds. And then also that portion of the molecule is at the end of it. So we will go ahead and have our methyl group, or CH3. And now that we're showcasing all of the hydrogens within our molecules in terms of those carbon-hydrogen bonds, we can now more accurately showcase all the sigma bonds that the molecule has. So we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sigma bonds. So we'll write that down, 13 sigma bonds. Now, in terms of pi bonds, visually, those are a lot easier to see because all we're looking for are either double bonds or triple bonds. And in this case, we have a double bond right here, and then a double bond right here. And if we were to go back to our chart, whenever you have a double bond, that has 1 pi bond. So if we were to count, we have a total of 2 pi bonds because we have 2 double bonds in our structure. So we'll go ahead and write down 2 pi bonds. And then in terms of the p orbitals, more specifically those unhybridized p orbitals, whenever you have 1 pi bond, those have 2 p orbitals that are forming the pi bond. And we can see right here, 2 p orbitals need to have that side-to-side overlap to form a pi bond. So since we have 2 pi bonds, 2 pi bonds times 2 p orbitals gives us a total of 4 p orbitals that are participating in that structure. Then we can move on to our next example. And yet again, we're just showcasing how many sigma bonds, pi bonds, and p orbitals we have. And if we were to go back to our original, to this example, we needed to include our hydrogens. So we'll go ahead and do that as well. So if we're looking at the end of a molecule right there, that should have 3 hydrogens coming off of it. Perfect. And if we're looking at this carbon right here, since that carbon is bonded to 2 other carbons, we'll go and add 2 bonds to hydrogens. And then we'll look at this group right here. If we're looking at this end carbon, it currently has 3 bonds because it is a triple bond. So that means we just have to include one more hydrogen in order for this carbon to have a total of 4 bonds. So now we can go through and count the sigma bonds because every single bond, whether it's a single, double, or triple, will have at least 1 sigma bond. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 sigma bonds. And just to kind of point it out, this one might be a little tricky, but this carbon is bonded to this carbon right here. So this is a single bond, and then right here is a triple bond because these 2 carbons have those 3 bonds with each other. And then this bond right here is just a single bond where our carbon has a single bond to that hydrogen. So that's where our 10 sigma bonds come from. And then in terms of our pi bonds, we can easily see this because we have a triple bond right there. And triple bonds, if we were to go back to our chart, those have 2 pi bonds. So in this example as well, we have 2 pi bonds. And then in terms of p orbitals, the number of pi bonds help us dictate the number of p orbitals we have because 1 pi bond consists of 2 p orbitals. And since we have 2 pi bonds, 2 times 2, we get 4 p orbitals again. Perfect. So now we will go into those hybridized orbitals. And hybridized orbitals are when your atomic orbitals kind of mesh together and form different orbitals called hybridized orbitals. So right here, oops, let me get my laser pointer out. Right here is where we're looking at those atomic orbitals where we have s orbitals and individual p orbitals. But for hybridized orbitals, these orbitals will come together and they can form things such as sp3 orbitals, sp2 orbitals, and then sp orbitals. So those are when, yet again, those s and p orbitals are meshing together to form orbitals that are the same in energy. So for example, these are all hybridized orbitals. They're the same in energy. Hybridized orbitals here, here, they're all the same in energy. Now, in terms of these hybridized orbitals, the number of atomic orbitals you put in gives you the number of hybridized orbitals you get out. So for example, sp3 orbitals, whenever we have that number above the p, that's telling us how many p orbitals we took to form those hybridized orbitals. So if we're looking at sp3 orbitals, that's telling us we had 3p orbitals and 1s orbital come together to form our sp3 orbitals. So if we were to look, we have 1s orbital, 3p orbitals. In terms of atomic orbitals, here are 4 atomic orbitals. And when we mesh those together, we get four hybridized orbitals. And then in terms of sp2 orbitals, 2, that's telling us we only took 2p orbitals to form our hybridized orbitals. So it looked like this, where we're snagging those 2p orbitals and the s orbital, and then we're leaving behind one of the p orbitals. And that consists of 3 atomic orbitals. And those 3 atomic orbitals gives us 3 hybridized orbitals. And this is what I was talking about in terms of unhybridized p orbitals. So this p orbital is the exact same p orbital that we started with all the way back up here. It's not going to hybridize. It'll be its own p orbital. And that'll be very important in terms of those pi bonds. And then for sp hybridized orbitals, that's where we only have one s orbital and one p orbital coming together to form a total of 2 hybridized sp orbitals. And since we only stole one p orbital, that means we left behind 2 other p orbitals that can be used for triple bonds or other bonds. Now, in terms of assigning hybridized orbitals, there is a trend in terms of the number of electron groups you have and the hybridization an atom should be. So just to review what an electron group is, it's basically just looking at the electron density that surrounds an atom, and that's looking at lone pairs and then also single, double, and triple bonds. So in this case, we can go through and assign the hybridization real quick just by looking at the electron groups. So if we're looking at this carbon right here, that is going to be sp3 hybridized because it has 4 groups surrounding that carbon. We have 1, 2, 3, 4. And this is a good example of whenever something, or more specifically, when a carbon is sp3 hybridized, it can have a tetrahedral geometry. And then if we're looking at this carbon right here and looking at the electron groups, it has 3 electron groups, which we have 1, 2, 3 right there. And I know that this is a double bond, but we still consider that one electron group because an electron group is just looking at the concentration of electrons in a specific space. These electrons are concentrated in that space, so we consider it one electron group. So since we have 3 electron groups, it'll be sp2 hybridized. And then if we're looking at this carbon right here, it has 2 electron groups, has 1 on the right, then this whole group on the left, it will be sp hybridized. And in terms of the structure and the geometry of something that is sp hybridized, don't forget that it has a linear geometry, and we have to showcase that in our bond line notation. So we'll go through a couple examples in terms of assigning hybridization. And for this, we will label the hybridization of each atom in the molecules that will be shown. So we'll go through and start with this carbon right here. Now, this carbon, we can't forget, has 3 other hydrogens coming off of it. And if we were looking at that carbon, it currently has 1, 2, 3, 4 electron groups coming off of it. And since it has 4 electron groups, that means it will be sp3 hybridized, just like that. And then we can move over to this carbon right here. In terms of the number of electron groups the carbon has, it has one, two, three electron groups, which means it'll be sp2 hybridized. But what about this oxygen? We have to remember that neutral oxygen will have two bonds and two lone pairs. So we'll go through and include those lone pairs. And by including those lone pairs, we see that we have one, two, three electron groups surrounding that oxygen. So the oxygen will also be sp2. And then what about this carbon right here? This carbon has three bonds to other carbons, which means we still have another hydrogen coming off of it. So that means it'll be sp3 hybridized, just like that. And in terms of these carbons right here, because each of those carbons will have two hydrogens coming off of them, since all of those carbons will have four electron groups surrounding the carbons, each of those will be sp3. So we'll go ahead and copy and paste those. And just to minimize confusion, these carbons are all equivalent in terms of how many hydrogens that are coming off of them. So since they all have four electron groups, that is why they're all sp3 hybridized. But what about these two carbons? Those two carbons still only have one hydrogen coming off of them because those carbons currently only have three bonds. So we can go ahead and draw those out. And if we're looking at the electron groups that are currently surrounding the carbon, we have one, two, three electron groups. And since we have three electron groups, that means they are sp2 hybridized. Perfect. Now, just to make a note real quick, you may be asking why are we not really including any hybridized orbitals for the hydrogens? And that is because hydrogens don't hybridize. They don't have any hybridized orbitals. Hydrogens are only composed of s orbitals. So that'll be something to keep in mind, especially for some of the examples we have later on. Now, for our next example, we can go ahead and start with this carbon right here. This carbon has two bonds to other carbons, which means it has two other hydrogens branching off of it. And if we're looking at the electron groups surrounding that carbon, we have one, two, three electron groups, which means it is sp2. And then that'll be the same idea with this carbon right here. It has one, two, three bonds, which means there's an extra hydrogen coming off of it. And by including that extra hydrogen, we can see that there will be a total of three electron groups, which means that the carbon will also be sp2 hybridized as well. And then let's look at this carbon right here. We see that we have three electron groups, which means it will also be sp2 hybridized. Perfect. And then similar to the structure above, oxygen, we will include those lone pairs because oxygen, when it's neutral, will have two bonds and two lone pairs. And in this case, we have three electron groups. So our oxygen is sp2 hybridized. And then let's look at this carbon right here. It has two bonds to other carbons, which means we have to include those hydrogens. I'm sorry if it's seeming very tedious or redundant if I'm including those hydrogens. I just want you to be comfortable by looking at a carbon, seeing how many bonds it has, and correlating how many hydrogens should be there. But this carbon is currently surrounded by four electron groups, meaning it's sp3 hybridized. And then if we're, I wrote down two, that should be a three, perfect. And then if we're looking at this carbon right here, the carbon has a negative charge. And whenever carbon has a negative charge, that's telling us that carbon has three bonds and one lone pair. So we'll go ahead and include our hydrogens and then our lone pair. So even though we have a lone pair on our carbon, this still means we have three electron groups surrounding that carbon, so it will still be sp3 hybridized. Perfect. So that's a good example right there. So I will say it'll be very common when you do start learning about some reactions, just whenever a carbon has a negative charge, that has a lone pair. It's a little difficult to see because we're so used to seeing our lone pairs on heteroatoms, but whenever you see a negative charge on carbon, it has a lone pair. And then we'll move on to our next example. We'll start at the very end of our molecule. Since we're at the end, that carbon has 3 hydrogens coming off, just like that, which means we have 4 electron groups, giving us sp3 hybridization. We'll write that down. And then in terms of this carbon right here, we still have 2 hydrogens branching off of it. That will also be sp3 hybridized as we have those 4 electron groups surrounding the carbon. And then in terms of our nitrogen, whenever we have neutral nitrogen, that means there's 3 bonds coming off of nitrogen along with a lone pair. And if we were to count our, there we go. If we were to count our electron groups surrounding the nitrogen, we have 1, 2, 3, 4 electron groups, meaning it is sp3 hybridized. And then if we're looking at this carbon, has 2 hydrogens coming off of it, giving us a total of 4 electron groups, meaning it's sp3 hybridized. And then if we're looking at these 2 carbons right here, those 2 carbons, both of them, have 2 electron groups coming off of them. So if we're looking at this carbon right here, we have an electron group coming off right here, and then another electron group over here as well. And that's going to be the same case with this carbon right here. Electron group on the left, electron group on the right. So both of those carbons, especially since they are participating in a triple bond, those will be sp hybridized. Include those. So whenever you have a triple bond, immediately think sp hybridization. Just like if you're looking at a double bond, the first thing you should think of is sp2 hybridization. And then we have this carbon over here. Since that's at the end of a molecule or the end of our chain, we have 3 hydrogens coming off of it, which means 4 electron groups, giving it sp3 hybridization. Include that with the carbon. Perfect. Now for our remaining questions, what we want to do is label the orbitals used in the indicated covalent bonds. So what does this mean? Each arrow is currently pointing at a specific bond, and if we recall back to those sigma and pi bonds, those sigma bonds are head-to-head overlap. Those pi bonds are weaker side-to-side overlap. Those are p orbitals only. But in terms of sigma bonds, not only can they be made with s orbitals and p orbitals, but we can also form them with hybridized orbitals. So let's look at this bond right here. What we need to do first is find the hybridization of each carbon that's forming the bond. So we'll look at this carbon right here. We see that it has 2 hydrogens coming off of it. And since we have 4 electron groups coming off of that carbon, that means it's sp3 hybridized. And then in terms of this carbon right here, it will have 1 hydrogen coming off of it, which means it has a total of 3 electron groups, making it sp2 hybridized. And now that we know the hybridization of our carbons that are forming the bond, we can go ahead and showcase which orbitals are making our bond. Now, in terms of the bond we have between these 2 carbons, it is a sigma bond only because it's just a single bond. So we'll go ahead and include our sign for a sigma bond. And this is a common notation that we'll see when you have to like label which orbitals are forming a bond. But for that sigma bond, we have our carbon right here, which consists of an sp2 orbital that is being overlapped with a carbon. Let me make some room for this notation real quick. There we go, perfect. So that carbon that is sp2 hybridized will be bonded to a carbon that is sp3 hybridized, just like that. So that's how we can label which orbitals are forming which bond. And just to recap, since we have a sigma bond right here, this is denoting that we're dealing and that we're representing a sigma bond. And that sigma bond is formed from a carbon with an sp2 orbital being bonded to a carbon with an sp3 orbital. So that's how we got our answer there. But up next, we have to assign which orbitals are forming this bond right here. So just like the carbon above it, this carbon right here will also be sp2 hybridized. So we'll showcase that. But what about the hydrogen? If we remember from earlier in the lesson, hydrogens are only participating when they form bonds, they're only using an s orbital. So in this case, to represent our sigma bond, we would have that sigma bond is being made of a hydrogen with its singular s orbital that is being bonded to a carbon with an sp2 orbital, which we can see right here. Carbon is sp2 hybridized, and then our hydrogen just has an s orbital. So that's where that sigma bond is coming from. But what about this bond right here? Now remember, whenever we're dealing with double bonds, we have at least one sigma bond, and we also have a pi bond. So we'll go ahead and write down those notations just so we're aware that we need to find both. So we have our sigma bond right there, and then we have our pi bond right there. So let's go through and find the hybridization of both our oxygen and our carbon. We can include those lone pairs on oxygen since it's neutral. To remind you, when oxygen has two bonds, it has two lone pairs. And since that's the case, we have three electron groups surrounding the oxygen, which means it's sp2. And then same thing with this carbon right here. Since it has three electron groups, it'll be sp2 as well. So now that we know which orbitals are, sorry, the hybridization of both our carbon and our oxygen, that's showcasing where that sigma bond is coming from. So our sigma bond is being formed between a carbon and its sp2 orbital, along with an oxygen in its sp2 orbital as well. Now, in terms of that pi bond, if we remember, pi bonds can only form with pi bonds can only form with p orbitals. And if we were to go back up to our chart up here, because I think it's a good example, whenever we have something that's sp2 hybridized, we have three hybridized sp2 orbitals, and then we have this single unhybridized p orbital up here. And that unhybridized p orbital is left behind so that it can form a pi bond. So this pi bond is being formed between a carbon p orbital. So we have a carbon p orbital along with an oxygen p orbital, just like that. So just to recap, since we have a double bond right here, it's composed of a sigma bond and a pi bond. That sigma bond is being formed between those hybridized orbitals, but then that pi bond is being formed between those p orbitals. And we'll move on to our next one. So we'll start on the left side and work our way towards the right side. So yet again, we'll go through, assign the hybridization of our molecules. And this carbon right here, it has three other bonds. So if we were to include that hydrogen, it now has four bonds that we can visually see, which means it has four electron groups surrounding it. So it will be sp3 hybridized. But what is the hybridization of chlorine? Chlorine, in terms of its orbitals, does not undergo hybridization. And whenever chlorine makes a bond with something, it's just bonding with one of its p orbitals. So we'll go ahead and write that down. It will have a p orbital that it's bonding with. So in terms of our sigma bond, since we only have a single bond between our carbon and our chlorine, we will write down our sigma sign. And that sigma bond is between a carbon's sp3 orbital along with a chlorine's p orbital, just like that. Now, in terms of pi bonds, those only occur when you have two p orbitals that have that weak side-to-side overlap, but it's okay to use one p orbital along with another p orbital to form a sigma bond, or a p orbital and a hybridized orbital to form those sigma bonds as well. And that's what we're showing right here. Now, what about this bond right here? This bond is a single bond, and since it's a single bond, we'll showcase our sigma notation. And let's look at the hybridization of those two carbons. that are making the bond. We have this carbon right here, which is sp3 hybridized, because the carbon would have two hydrogens coming off of it. But then this carbon right here is only sp hybridized, because remember, whenever a carbon is participating in a triple bond, which this carbon has a triple bond with this carbon right here, it will have an sp hybridization. So we'll go ahead and write that down, which means our sigma bond is between a carbon's sp3 orbital and then another carbon's sp orbital. Perfect. But now let's look at the bonds that are making, let's look at the orbitals that are making this triple bond right here. Now, whenever we have a triple bond, that means we have a sigma bond along with two pi bonds. So we'll go ahead and write down a sigma bond and then our pi bonds as well. Perfect. And then in terms of the hybridization of this carbon, we already know that it's sp hybridized. But then in terms of this carbon right here, since it's participating in that triple bond, it will also be sp hybridized, just like that. So for this one, it's easy. Our sigma bond is being made between a carbon's sp hybridized orbital along with another carbon's sp hybridized orbital. And then in terms, remember, pi bonds only form between p orbitals with that weak side-to-side overlap. So our pi bonds are made between a carbon p orbital and then a carbon p orbital. And then same thing, since we have two pi bonds, that means we're using a total of four p orbitals to make those two extra pi bonds. And this is a good example of showcasing that chart I had earlier. Whenever we have something that's sp hybridized, we have our sp hybridized orbitals, and then we leave behind those two p orbitals, which can make pi bonds. And then for our last example right here, we'll go through and label which orbitals our indicated lone pairs are in. So let's start with this oxygen right here. In terms of the electron groups we have 4 electron groups, which this one is easy. That means it is sp3 hybridized. But in terms of this lone pair right here, it can be tricky, but yet again, we can just go through and count our electron groups. We have 1, 2, 3 electron groups. And since we have 3 electron groups, that means it is sp2 hybridized. And in terms of this pi bond right here, remember, pi bonds can only form between p orbitals, and it would make sense for this nitrogen to be sp2 hybridized, because if we remember, when something is sp2 hybridized, we have a remaining p orbital that's left behind, and that remaining p orbital is currently being occupied by the pi bond that nitrogen has with this carbon. So that's a good example and a good refresher in terms of pi bonds are only used for p orbitals, even if we have a lone pair left behind. That'll have a lot of implications when we start talking about resonance starting next week. But speaking of resonance, I just wanted to give you guys a brief introduction in terms of what to expect. I know that in Gen Chem, you looked at resonance as if like, oh, this double bond could technically be between this carbon and oxygen, or it could be between this carbon and oxygen. But in terms of organic chemistry, we're not really looking at resonance in terms of, oh, the double bond could be in different places. When we start learning about resonance in terms of organic chemistry, we're more so talking about the delocalization of electrons through a pi system. So it's not that, oh, these double bonds could be drawn in different places, or we can have multiple different Lewis structures. It's more so looking at how those electrons can spread out throughout the entire pi system of a molecule. And we'll do a deep dive into that next week. And that'll be the main topic of next week's session, will be resonance. But then also for those premium users or any users in general, if you guys do have any questions, feel free to submit them before the session, and I would love to answer them during the live stream. But besides that, I'll hand it off to you, Melissa.
Yeah, thank you so much, Cooper. This was great to go over orbitals. I know a lot of students don't remember to go over that. And then you guys also got a glimpse of what the first topic that you'll learn in organic chemistry that's different. I also want to put in the chat right now just some links to help you guys review more if you feel like after the session, oh man, I really need to start reviewing this, or if you feel just ready to move on, then go ahead and look at everything that I sent you there. I'm just also going to put this on the YouTube side as well, just so you guys can see what I'm talking about. So perfect. And then I'm also going to do one more link. So that top link is just the general chemistry review. So that's everything I recommend you know before walking into class. And then that other link, that structure and bonding, is the main first chapter that you actually cover that's brand new for organic chemistry. So if you're ready to jump into that, go ahead and start. For next session again, it's going to be at the same exact time. So next Monday for Organic Chemistry 1. And as Cooper mentioned, he will be going over resonance. But of course, if you guys have questions, you have that opportunity as community members to be able to ask those questions and get them answered. Cooper will be more than happy to answer that and go over it for the following week. So again, that's going to go live on that like community page. You'll get a notification on it, but that will go live on Thursday so that you guys can post your questions there, whether it's just a specific topic you want to cover again, or if you even have an image of whether it's a homework assignment or something else, then go ahead and post that there. The other great thing about being a premium member is the fact that you will be able to ask those questions and get them answered. So let's say if you struggled with an exam and now you wanted to look back and see what in the world did I get wrong? Why was this incorrect? Then we can go over those test corrections in our sessions. Same with any quizzes that you cover and whatnot. But thank you so much for being here, and I hope to